6 easy pieces. Essentials of Physics, explained by its most brilliant teacher, by Richard P. Feynman, Robert B. Leighton, and Matthew Sands.
Yes.
That is exactly what we're diving into today. And, I mean, we're obviously talking about Richard P. Feynman here. He's the principal physicist, the lecturer, really the defining scientific voice of all these ideas.
Yeah, absolutely.
But it is crucial that we preserve Robert B. Leighton and Matthew Sands as his fully credited collaborators.
Yeah,
Because they really helped construct this entire monumental work.
they did. And our intention for this deep dive is to tackle one massive overarching question.
Let's hear it.
How can a small set of foundational ideas, including atoms, energy, gravitation, quantum behavior, and the unity of the sciences, explain the immense variety of phenomena in the physical world?
It's a huge question. And before we get totally into the weeds here, let me just give you a sense of where we're going today.
Yeah, give us the roadmap.
Because we are looking at how a few simple rules build literally everything. And I mean everything. The same underlying mathematical logic that explains why a dropped coffee mug shatters on your kitchen floor is the exact same logic explaining why time only moves forward and why the stars will eventually burn out.
All connected.
Exactly. So we're going to start microscopic, really looking at the invisible jiggling of atoms.
Okay.
Then we'll scale up to everyday motion, pull the camera way back to the cosmos to look at gravity,
Right.
and then dive all the way down into the quantum realm where reality gets genuinely weird.
Very weird.
And finally, we'll see how physics weaves into biology and chemistry without just erasing them.
It is an ambitious path.
Yeah.
But, before we can even begin to apply these rules to stars or coffee mugs, we really have to define what a rule actually is.
Right.
When physicists talk about a physical law, they are really talking about compression without oversimplification.
Okay, let's unpack this. Because when I hear the word law, I think of an absolute unchanging truth.
Sure.
But you're talking about compression. So is a physical law kind of like a map?
Yes, exactly.
Like a map of New York City is incredibly useful because it compresses the chaos,
Right.
but it leaves out the individual hot dog stands and the cracks in the sidewalk so you can actually read the subway lines.
That analogy perfectly captures the spirit of physics. A physical law takes a chaotic, everyday experience.
Like apples falling.
Exactly. Apples falling or the moon moving across the sky, and it compresses it into a quantitative principle. But a map operates using models and approximations, and so does physics.
Yeah.
We might mathematically treat a planet as a single point of mass, or we might calculate the fall of an object while entirely ignoring air resistance.
Which works great if you're dropping a bowling ball.
Right.
But if you drop a feather, your map is completely useless at that point.
Right.
Because the neglected effect of air resistance just isn't small anymore.
Which brings us to the ultimate reality check for any physical law, which is measurement.
Okay.
You can have a beautiful equation, you get a perfect mathematical map. But in science, it is entirely meaningless until you connect it to physical measurement.
And a measurement is never just a naked number, right?
No, absolutely not. It requires units, a calibrated instrument, and an explicit limit of uncertainty.
I want to pause on that word uncertainty, because I think a lot of people hear uncertainty in science and assume it means they don't know what they're talking about.
Yeah.
Like it's just a best guess.
That is a fundamental misunderstanding of the term. In physics, uncertainty isn't an admission of ignorance.
Okay.
It is a highly precise quantification of knowledge. It defines a rigorous boundary based on known sources of variation in your instruments and your methods.
Right, so it's a feature, not a bug.
Exactly. If a physicist gives you a measurement without that defined limit of uncertainty, they haven't made a complete scientific statement.
Oh, wow.
You have to know exactly how precise your map is before you try to navigate with it.
And demanding that level of precise measurement is really what allowed scientists to establish the foundation of everything we're talking about today, right?
Yes.
The atomic hypothesis.
The realization that ordinary matter is made of atoms.
Right. But I think we need to do some demolition work here first.
Oh, definitely.
Because we all have this image ingrained in our heads from grade school science fairs.
I know exactly what you're going to say.
The atom as a tiny solar system,
Yeah.
a big nucleus in the middle like the sun, and little electrons whirling around it in perfect planetary orbits.
We need to discard that image immediately.
Just throw it out.
Throw it out. Atoms are absolutely not miniature classical solar systems. It's a fundamentally misleading lecture.
Okay.
The electrons do not travel in little planetary tracks. That classical orbital mechanics model completely breaks down at the microscopic scale.
So what are they doing then?
Atoms are governed entirely by quantum theory. which operates under very different rules that we will get into later.
Okay, okay. But if we can't trust that classic drawing, and a single atom is far too small to just look at through a standard optical microscope,
Right.
how did we actually prove they were there? I mean, nobody just took a really good photograph and said, aha, atoms.
No, they didn't. The proof came from a convergence of independent methods. Think of it like trying to prove an invisible crowd is in a stadium.
Okay.
You can't see the people, but you notice a giant inflatable beach ball randomly jerking around and bouncing above the seats.
Oh, Brownian motion.
Yes. When scientists looked at tiny particles like pollen suspended in water,
Through a microscope.
right, through a microscope,
Yeah.
they saw them constantly dancing and zigzagging in random directions. You can't see the water molecules, but the erratic movement of the pollen tells you it's being bombarded by millions of invisible moving particles.
That makes total sense.
And you combine that with crystallography, where the angles of crystals suggest stacked building blocks.
Yeah.
And spectroscopy, which shows light being emitted at very specific quantized frequencies. All these entirely different observations pointed to the exact same microscopic architecture.
It's like having a dozen independent witnesses who all viewed a car crash from different buildings, and their stories perfectly aligned. So, if we accept this reality, that everything is made of these quantum entities vibrating and moving, how does that invisible chaos create the world I can actually feel? Like, if I wrap my hands around a hot mug of coffee, what is physically happening?
You are feeling the statistical distribution of microscopic kinetic energy.
Okay, words. What does that mean?
It means when you say something is hot, you aren't detecting a glowing fluid flowing into your hands. You are feeling thermal motion.
The jiggling.
The jiggling. The atoms in that coffee mug are jiggling violently. When you touch it, that violent jiggling bumps into the atoms in your skin, transferring kinetic energy.
Oh, I see.
Temperature is just a way to describe how that energy is distributed among the molecules.
Yeah.
Broadly speaking, more heat means a wider distribution of faster, more violent microscopic speeds.
So temperature is just a measure of the jittering.
Basically, yes.
What about pressure then? If I take a balloon and squeeze it, it pushes back.
Right.
Is that just the atoms acting like tiny compressed springs against my hand?
Not springs. It's billions of tiny car crashes.
Car crashes.
Inside that balloon, countless gas molecules are flying around at hundreds of miles per hour, constantly colliding with the rubber boundary.
Wow.
Each individual collision transfers a microscopic bit of momentum. But when you aggregate billions of those collisions every fraction of a second, it manifests as a steady macroscopic force pushing outward.
Okay, so when I squeeze it,
If you squeeze the balloon to half its size, you force the same number of molecules into a smaller space. They hit the walls more frequently, and the pressure goes up.
and this constant microscopic battle, the violent jittering of thermal motion versus the binding interactions trying to hold atoms together,
Yes.
is that what dictates whether something is a solid, a liquid, or a gas?
That is exactly the core of phase changes.
Okay.
In a solid piece of ice, the binding interactions between the water molecules are strong enough to overpower the thermal jittering.
So it holds its shape.
Right. The structure stays rigid, but as you add heat, you increase that jittering.
The jiggling gets violent.
Very violent. And eventually, the thermal motion becomes violent enough to break those rigid bonds. The molecules can now slide past each other.
Which is melting. The water molecules themselves aren't melting, right? The H2O is perfectly intact.
Correct. It's just the collective arrangement changing from rigid to fluid.
And if you keep heating it.
The jittering eventually completely overpowers the binding interactions, and the molecules fly apart to become water vapor, a gas.
But what about when a glass of water is just sitting on a desk at room temperature? It looks completely still.
Macroscopically, it is in equilibrium. But microscopically, it is an absolute war zone.
A war zone.
Water molecules are constantly gaining enough random kinetic energy to break free and evaporate into the air.
Oh, wow.
While water vapor molecules in the air are constantly crashing back into the surface and condensing.
Wait, really? So it's happening in both directions at once?
Yes. Equilibrium doesn't mean everything stopped moving. It just means the score is tied. The rate of evaporation perfectly matches the rate of condensation.
That is wild to picture. So what does this all mean for a whole field like chemistry? If a chemical reaction is really just the rearranging of electron densities and quantum energy landscapes,
Right.
is chemistry just physics in disguise? Like, can a chemist just retire and hand their lab over to a physicist?
No, absolutely not. Explaining a chemical system through physical mechanisms does not make chemistry unnecessary.
Okay.
This is a crucial concept in science called explanatory pluralism.
Explanatory pluralism.
Yes, physics dictates the foundational rules. But if you want to understand how a complex protein folds, or how a specific functional group reacts, trying to calculate the quantum trajectory of every single electron is computationally impossible.
And probably useless.
Practically useless, yes.
Mhm.
Chemistry develops autonomous concepts like acidity or molecular recognition that efficiently solve chemical problems.
Right.
Physics grounds and constrains chemistry, but it does not erase the need for it.
Okay, so whether atoms are just changing phases from ice to water or undergoing a violent chemical reaction, things are constantly transforming.
They are.
But beneath all that chaos, there is a strict bookkeeping system in nature, right? Like certain things never change.
You are referring to conservation laws.
Yes.
In a closed system, a conserved quantity is one that remains absolutely constant no matter what internal transformations occur.
So if something appears to be lost or missing,
It hasn't vanished from the universe. It is merely transferred to an untracked form, like heat or ambient radiation.
and the undisputed king of these rules is the conservation of energy.
Definitely.
But I feel like we need another demolition job here.
Let's do it.
Because pop culture has completely ruined how we visualize energy.
Oh, completely.
In every sci-fi movie, energy is this crackling, glowing blue fluid. They route it through pipes, it leaks out of reactors, it charges up laser cannons.
It is a very pervasive misconception.
Yeah.
Energy is not a material substance. It isn't a glowing fluid. And it isn't a physical mechanism that pushes matter around.
Then what is it?
Energy is an abstract, mathematically conserved quantity. It is a bookkeeping metric. We use it to track transformations across kinetic motion, potential fields, and mass.
It's like money.
Like money.
Yeah, a $20 bill is a physical object, but the value of $20 is an abstract concept we use for bookkeeping.
That's a great way to put it.
Like, you can store your wealth in a house, you can hold it in gold bars, or you can have it sitting in a digital bank account. The form constantly changes, but your total net worth, the bookkeeping metric, is conserved.
That is a very effective way to look at it. Consider potential energy.
Okay.
If you push a boulder to the edge of a cliff, the boulder doesn't suddenly contain a glowing orb of energy inside it.
Right.
The potential energy is a property of the entire interacting configuration.
The boulder and the cliff.
The boulder, the Earth, and the gravitational field between them. It encodes how gravity will exchange that configuration for kinetic motion if you push the boulder off the ledge.
So the bookkeeping tallies up perfectly.
Perfectly.
But if the bookkeeping is always perfect, if total energy is always conserved before and after an event, why can't a shattered glass spontaneously put itself back together?
Ah.
Because if a glass falls off a table and shatters into 100 pieces on the floor, all the energy is still right there in the room, right?
It is.
The sound waves, the heat in the floorboards, the kinetic energy of the shards, why doesn't it all just perfectly reverse and fly back up onto the table?
Because conservation of energy tells you the totals are the same before and after. But it does absolutely nothing to explain why a process occurs, or why it has a preferred direction.
Interesting.
The first law of thermodynamics, energy conservation, does not forbid the glass from reassembling.
Wait, really? It doesn't forbid it?
No. For that, we need the second law of thermodynamics.
The law of entropy.
Yes. The second law introduces the multiplicity of microscopic arrangements. Think of a brand new deck of playing cards, perfectly sorted by suit and number.
Okay.
If you throw that deck into the air and let the cards scatter across the floor, what are the odds they land perfectly sorted again?
0.
Effectively 0. Not because physical laws forbid them from landing in order, but because there's only one specific arrangement that is perfectly sorted, and billions upon billions of arrangements that are a messy, random pile.
Wow.
Entropy is a measure of that microscopic disorder. For a shattered glass to reassemble, millions of tiny thermal vibrations in the floor would have to spontaneously, randomly align in the exact reverse trajectories to launch the shards perfectly back together.
Which is just statistically impossible.
The universe moves toward disorder simply because there are astronomically more ways to be messy than there are to be perfectly organized.
Which is why time has an arrow, why we remember the past and not the future.
Exactly.
So we've got the microscopic world sorted, and we understand nature's bookkeeping. Let's start looking at the stuff we can actually see moving, everyday motion.
Sir Isaac Newton,
The man himself.
Newtonian mechanics gave us the conceptual framework for macroscopic motion: inertia, force, and interaction pairs.
Right.
The principle of inertia was revolutionary. It states that rest and uniform straight-line motion are not fundamentally different states.
Okay.
An object moving at a constant speed doesn't need a force to keep it moving. It only needs a force to change its motion.
And those forces always occur in pairs, action and reaction.
Yes.
But this is another area where our daily intuition actively sabotages us, I think.
How so?
Well, when a rocket launches into space, a huge portion of people assume the fiery exhaust is pushing against the launch pad or pushing against the air to lift the rocket. But there's no air in space.
Right. Rocket propulsion has nothing to do with pushing against the atmosphere. It is purely governed by the conservation of linear momentum.
Okay, explain that.
A rocket works by throwing mass, the incredibly hot exhaust gases, backward at tremendous speeds, because the total momentum of the closed system must remain zero.
Oh, I see.
If you throw a massive amount of momentum in one direction, the rocket body must gain an equal amount of forward momentum in the opposite direction.
Mm-hmm.
The rocket is exchanging momentum with its own exhaust.
It's like standing on a skateboard with a heavy bowling ball. If you throw the ball forward as hard as you can, you're going to roll backward.
Perfect analogy.
Not because the ball pushed on the air, but because of recoil.
Yes.
But wait, let me push back here. We've known for over a century since Einstein that relativity is real.
We have.
We know at high speeds and huge masses, Newton's rules start breaking down. So if Newton was technically wrong, why is this still taught? Why don't we just use relativity for everything?
Because Newtonian mechanics remains an exceptionally accurate approximation for everyday speeds and macroscopic scales.
Oh.
Returning to our earlier analogy, a new, highly detailed satellite map does not make your simplified subway map useless. If you are an engineer building a suspension bridge or a NASA planner calculating a trajectory to Mars, you use Newtonian calculations.
Oh, NASA still uses it.
Oh, yeah.
Yeah.
In those specific domains, the relativistic corrections are so vanishingly small they are completely irrelevant. Physics is about knowing the domain of your tools.
And Newton's most famous tool was his law of universal gravitation, the inverse square law.
Yes.
Before Newton, humanity basically assumed the heavens operated on some kind of divine, magical rule book completely separate from the mud and rocks down here on Earth.
True.
Newton's genius was realizing that the mathematical force pulling an apple out of a tree is the exact same force tethering the moon in its orbit.
It was one of the greatest conceptual unifications in human history. The inverse square geometry beautifully describes an influence spreading out symmetrically through three-dimensional space.
Okay.
The further away you get, the area that influence has to cover expands by the square of the distance.
So it gets weaker, but predictably weaker.
Exactly. And this elegantly explained Kepler's laws of planetary motion.
Which were?
Things like why planets sweep out equal areas in equal times, why they accelerate as they get closer to the sun, and the exact mathematical link between a planet's orbital period and its distance.
Which sets up one of my favorite mind-bending realizations in all of physics: weightlessness.
Oh, this is a good one.
When you watch video of astronauts floating around on the International Space Station doing flips and eating floating blobs of water, it looks like gravity just got turned off.
It does look like that.
But the ISS is only about 250 miles up. Earth's gravity is still incredibly strong up there.
It is nearly as strong as it is on the surface.
Right. Really?
Yes. The astronauts are absolutely not floating because they have escaped gravity. They are in a continuous state of free fall.
This is where I want the listener to really feel the vertigo of this concept. The astronauts are plummeting toward the Earth.
Plunging directly toward the surface, yes.
Right.
But the spacecraft was launched sideways at roughly 17,500 miles per hour. They are moving horizontally so fast that as they fall downward, the spherical surface of the Earth curves away beneath them at the exact same rate.
So they just keep missing it.
They're perpetually falling, but constantly missing the ground. Because the astronauts and the space station are falling together at the exact same acceleration, there is no relative force pushing them against the walls or floor. Hence, apparent weightlessness.
Just a perpetual, silent, sideways skydive.
Yes.
It's terrifying and beautiful. But as elegant as Newton's math is for orbits, we have to address another misconception here. Newton's gravity is not the final boss of physics.
Far from it. While Newtonian gravitation is an incredibly useful approximation, it is not the fundamental theory of gravity.
Okay.
Newton could describe how gravity operated mathematically, but he had no idea what it was.
He just viewed it as an invisible tether pulling across empty space.
Right. And Einstein's general relativity replaced that tether entirely.
Right.
Einstein showed that gravity is the dynamical geometry of space-time itself.
This is usually where someone brings out the bowling ball on a rubber sheet analogy, right? The heavy ball creates a dip in the sheet, and a smaller marble rolling past gets caught in the dip and spirals inward.
Exactly. Matter tells space-time how to curve, and space-time tells matter how to move.
I've always loved that phrase.
With the caveat that a two-dimensional rubber sheet is a very limited way to visualize four-dimensional space-time, of course.
Of course.
But general relativity succeeds exactly where Newton failed. It perfectly predicted the anomaly in Mercury's orbit.
Oh, right.
It predicted time dilation, black holes, and the existence of gravitational waves, ripples in the fabric of space-time itself.
But even with Einstein's brilliance, we hit a massive brick wall.
We do.
Because general relativity gives us a stunning, highly accurate map of the cosmos. But if we try to use that map to navigate the microscopic world we talked about earlier, it bursts into flames.
It really does.
We do not have a working, experimentally confirmed quantum theory of gravity.
It remains one of the great open frontiers in modern physics. Gravity dominates the cosmos because it is a long-range force, and it is always attractive. It just keeps adding up.
Yeah.
But as we zoom down past the cell, past the molecule, into the atomic nucleus, gravity is absurdly, hilariously weak.
Like it doesn't even matter at that scale.
It cannot explain the architecture of an atom.
Yeah.
To understand what holds matter together, we need the Standard Model and the rules of quantum behavior.
Here's where it gets really interesting. The subatomic web.
Yeah.
Because down there, gravity takes a back seat to three other forces.
Electromagnetism, which drives chemistry and light.
Yeah.
The strong interaction, which acts like superglue holding the atomic nucleus together.
And the weak interaction.
Which is responsible for radioactive decay.
Yeah.
And all of these forces operate via fields that carry energy and momentum locally.
But when we actually try to observe how matter behaves in this microscopic realm, our everyday macroscopic intuition completely fractures. It's the famous wave-particle duality, the idea that a single electron is acting like a tiny billiard ball 1 second, and a rippling wave in a pond the next. Like it's quickly changing costumes in a phone booth depending on what the scientist wants to see.
We must correct that framing immediately.
Oh, is that wrong?
Yes. Quantum objects are not ordinary classical particles, and they are not ordinary classical waves. They are not changing costumes.
Okay.
Wave-particle duality is simply a shorthand way of admitting that our macroscopic classical categories are utterly inadequate to describe quantum reality.
So we just don't have the words for it.
Right. In experiments like the famous double-slit experiment, we see both behaviors simultaneously in a way that defies classical logic.
Right. If you fire individual electrons through a barrier with 2 slits in it, they hit the detector screen on the other side in localized individual dots. Like tiny paintballs? That looks like a particle.
It does.
But if you fire enough of them over time, those individual dots build up an interference pattern, a pattern of stripes where the electrons hit heavily, separated by dead zones where they never hit at all.
Which is bizarre.
And interference is the absolute hallmark of a wave overlapping with itself.
Exactly. To calculate where the electron might end up, we have to use the mathematics of probability and complex amplitudes. We assign an amplitude to every possible alternative path the electron could take.
Okay.
And those mathematical amplitudes can interfere with each other, amplifying the probability of the electron hitting a certain spot or completely canceling out the probability of it landing in a dead zone.
And this brings us to what might be the most abused, heavily distorted concept in all of popular science.
Oh, no.
The observer effect.
Yes.
The mystical idea that reality doesn't actually exist unless a human being is looking at it. That the electron somehow knows it's being watched by a conscious mind and decides to act differently.
This requires a very firm correction.
Let's do it.
Quantum measurement has absolutely nothing to do with human consciousness.
Good.
When physicists use the word observation or measurement, they're not talking about a person looking through a lens. They're talking about a physical interaction that creates a correlation.
Like a collision.
Exactly.
Yeah.
If you put a mechanical detector at one of those slits to see which way the electron goes, that detector has to interact with the electron, perhaps, by bouncing a photon off of it.
Right, it has to physically touch it in some way.
Yes. And that physical interaction reduces or destroys the delicate coherence between the alternative paths. The environment effectively gets entangled with the system.
So it's not about knowing, it's about touching.
A stray air molecule, a piece of the detector, a random photon, Any physical interaction that leaves a record will collapse that interference pattern. Consciousness is entirely irrelevant to the mechanics.
It's a relief to get that straight. The universe isn't waiting for us to look at it to exist.
No, it's not.
But this physical reality does mean that uncertainty is hardwired into the universe, right? It's not just that our microscopes aren't powerful enough.
Correct. Heisenberg's uncertainty principle tells us you simply cannot have arbitrarily sharp distributions for certain pairs of properties, like position and momentum, at the exact same time.
So you can't know both perfectly.
The more strictly you pin down an electron's location, the wilder and less defined its momentum becomes.
Wow.
It is a fundamental structural feature of nature, not an experimental bug.
Okay.
And while the predictive mathematics of quantum mechanics, using tools like the Born rule for probabilities, are incredibly precise and has been tested to astonishing accuracy, physicists maintain interpretive restraint.
What do you mean by that?
You can argue philosophically about the Copenhagen interpretation, or many worlds, or pilot wave theories, but the underlying predictive success of the mathematical framework remains exactly the same, regardless of your preferred philosophy.
The math works even if we don't know what the math means. So let's pull all of this together. We've gone from the probabilistic haze of quantum fields, up to the violent jittering of atoms, through the rigid bookkeeping of thermodynamics, and out to the curvature of spacetime.
It's quite a journey.
If physics is the ultimate foundation of reality, how does it relate to all the other sciences? Like, if I'm studying a biological cell, am I really just studying extremely complicated applied physics?
No, and treating it that way entirely misses the profound concept of emergence.
Emergence.
Explaining biological, chemical, or geological systems physically does not make those higher-level sciences unnecessary. We return to explanatory pluralism.
Meaning we absolutely need different vocabularies for different scales of reality.
Precisely. Look at biology. When you study how a heart pumps blood or how fluid dynamics allow a bird to fly, you are looking at emergent stability.
Okay.
The higher-level organization of the heart naturally constrains the lower-level physical processes without ever violating the underlying microphysics. A biological cell relies on thermodynamics, diffusion, energy conversion, and molecular machinery, all governed strictly by physics.
Yeah.
But you cannot explain a heart's pumping function simply by listing the quantum trajectories of its trillions of quarks. You need the systemic biological context to understand the function.
It's downward constraint. The structure of the whole system affects how the individual parts are allowed to behave.
That's a great way to summarize it.
And we see this unified tapestry everywhere, right? In geology, the Earth is a massive physical engine driven by thermodynamics, gravity, and radioactive decay.
Which gives us the grand mechanics of plate tectonics.
But if you want to understand the specific historical formation of the Alps, you need geological field evidence.
You do.
Yeah.
And in astronomy, light acts as a cosmic messenger, bringing us quantum spectra from billions of light years away.
Right. We use the quantum physics of atoms to deduce the chemical makeup of an alien atmosphere from a telescope.
Physics supports, grounds, and constrains all these higher-level sciences. But it requires them in order to fully describe the breathtaking complexity of the macroscopic world. The universe is unified, but understanding it requires a plurality of explanations.
And it is incredible how well this foundational framework has held up. Because if we look at the modern landscape up through August 2026, the bedrock principles we've discussed haven't been overthrown, but the details have become vastly richer.
They have. The triumphs of the Standard Model are a perfect example.
Like the Higgs boson.
Yes. The experimental confirmation of the Higgs boson, which explains the mechanism of mass, wasn't known when these foundational ideas were originally taught.
Right.
We have precisely mapped the cosmic microwave background, capturing the thermal echo of the Big Bang. We have directly detected gravitational waves hearing black holes colliding billions of light years away.
That still blows my mind.
It's amazing.
And we've taken quantum weirdness out of the realm of philosophical puzzles and turned it into actual engineering.
Yes, we are manipulating quantum interference and entanglement to build modern quantum information technologies. Sensors, cryptography, processors.
We are engineering with the uncertainty.
But none of those brilliant modern updates invalidate the foundational architecture we've been exploring today.
Which brings us to the ultimate synthesis of this deep dive. If there is one core takeaway from all of this, it is that a remarkably compact set of physical principles can explain an extraordinary range of natural phenomena.
Yes.
But that is only true when we rigorously understand their specific domains, the necessary approximations, the scales they operate on, and their vital connections to higher level sciences.
It's about learning how to think like a physicist.
Which means what, practically?
You ask what is strictly empirically measurable. You translate vague ideas into defined system changes. You estimate first, finding the order of magnitude before you get hopelessly lost in the weeds of an exact calculation.
Right.
You actively seek counterexamples to test the absolute limits of your assumptions. And above all, you preserve your curiosity and your humility.
I love that.
You accept that some answers remain entirely unknown, and you let uncertainty quantify exactly what it is you do know.
And before we pose our final question to the listener, it is required that we state clearly this production is an independent COSMORA HQ book overview in audio podcast format.
Right.
It is not an audiobook, complete narration, adaptation, abridgment, reconstruction, authorized edition, or substitute for the original book or the Feynman Lectures on Physics.
We strongly encourage listeners to seek legal access to the original work for the credited writer's complete presentation.
Absolutely. Go read the original. It is an absolute masterpiece of scientific communication. So we've traveled from the invisible jiggling of atoms, through the unbroken laws of energy, out to the warping of space-time, and down into the probabilistic quantum web.
It's been a ride.
And we want to leave you with this to ponder. Which foundational idea changes your understanding of the physical world most? Atoms, energy conservation, gravitation, quantum behavior, or the unity of the sciences?